Okay, let's dive right into this explainer. Think about it for a second. Electricity is literally everywhere. It's powering the phone in your hand right now, maybe a heater in your room, but it's completely invisible, right? You can't see it with the naked eye. Well, today we're going to change that. We're going to make the invisible forces of electricity visible.
To do that, we're going to build up our understanding step by step. We'll start with the flow of charge, then look at potential difference, electrical resistance, Ohm's law and its graphs, and finally, wrap it up with how all this applies to real-world materials.
All right, Section 1, the flow of charge, or moving electrons.
So to actually get what electricity is, we have to know exactly what's zooming around inside a wire when you flip a switch. It boils down to this. Current is simply the rate that free electrons are flowing through a metal. We write this mathematically as I equals Q over T, meaning charge divided by time, and we measure it in amps or amps. Now, here's a really funny historical quirk. Even though it's the negatively charged electrons doing the actual physical moving, we conventionally measure the current's direction as flowing the exact opposite way. Crazy, right? But it's a rule we still use today.
Okay, moving right along to Section 2, potential difference, the electric push.
Because look, electrons don't just decide to move on their own. They need a serious push to get going. Think about gravity. If you hold an apple and let go, it falls because there's a difference in height, right? It absolutely needs that drop. Electricity is exactly the same. Just like a falling object needs a height difference, an electric charge needs an electric potential difference to actually flow from one end of a wire to the other. So how do we measure that push? With volts. Potential difference is just a fancy way of saying the amount of work done to move a charge around a circuit. To be super precise, 1 volt is the potential difference when exactly 1 joule of work is done to move a charge of 1 coulomb. It's the sheer raw energy shoving those electrons forward.
Next up, Section 3, electrical resistance, or as I like to call it, the microscopic obstacles.
See, as those charged particles are flying through the wire, it is definitely not a smooth ride. They actually face a microscopic obstacle course. We call this resistance, and we measure it in ohms. Moving electrons are constantly crashing into fixed positive ions in the metal. So think about it. A longer wire, that means a longer obstacle course, so more resistance. A thinner wire, meaning a smaller area of cross-section, means less room to squeeze through. And if you heat the wire up, those fixed ions vibrate wildly, causing way more crashes. Plus, the actual nature of the material itself matters, since subsubstances naturally just have fewer free electrons to work with.
All right, Section 4, Ohm's law and graphs. This is where we unite these forces.
Ohm's law is the grand unifier. It tells us that the electric current is directly proportional to the potential difference across its ends, assuming the temperature stays the same. The famous formula, V equals I times R. And engineers physically verify this law using a very specific circuit setup. You've got a battery providing the push, a voltmeter checking the potential difference, an ammeter tracking the flow, and a rheostat to dial the resistance up or down. Now what's super cool here is how that math actually translates into geometry when you graph it. If you have an ohmic conductor like copper or silver, they play by the rules perfectly. You get this beautifully straight, linear slope. But if you look at a non-ohmic conductor, like a diode valve, its voltage to current ratio shifts around, giving you this sweeping curve instead of a straight line.
And hey, remember a minute ago when we said heat increases resistance because of all those atomic crashes? Well, check this out. This graph proves it visually. We're looking at the same conductor at 2 different temperatures. The steeper straight line, T1, has a higher resistance than T2. This tells us unequivocally that resistance shoots up at that hotter temperature, T1.
Okay, now that we've got the physics down, let's look at a real everyday mystery in your own house. Why does a light bulb's filament glow so brightly, pumping out all that heat and light, but the wire hooked right up to it, carrying the exact same current, stays totally cool and dark? How does that work? The secret is all in the materials, which brings us to our final stop, Section 5, Real-World Materials and Engineering with Physics. This breaks down the brilliant engineering behind the stuff you use every day. Your thick copper or aluminum connection wires, they have incredibly low resistivity, so electricity just glides through without making heat. But that little filament inside your bulb, it's made of tungsten. Tungsten has huge resistivity and a super high melting point. It's literally fighting the flow of electricity, which generates intense glowing heat, but it doesn't snap. It's the same idea for other stuff around your house. Standard resistors use manganese because its resistance is barely affected by temperature. Your fuse uses a lead tin alloy, so it will melt quickly and break the circuit if things get dangerously hot. And your space heater, that uses nichrome wire, specifically chosen for its high resistivity to keep your room toasty.
Let's do a super quick calculation to lock this all in. By plugging these real-world components into Ohm's law, V equals I times R, we can easily find resistance. Say a car bulb is connected to a standard 12-volt battery, and it's drawing 2 amps of current. We just divide the 12 volts by the 2 amps, and boom! We instantly know that the bulb's tungsten filament has exactly 6 ohms of resistance while it's glowing.
But wait, there is one mind-blowing exception to everything we just talked about: superconductors. These are rare substances that hit exactly zero resistance, but only at extremely low temperatures. For example, if you supercool mercury down to 4.2 Kelvin, it transforms. Suddenly, electricity flows completely unimpeded. No collisions, no heat lost. Just pure, perfect flow. Which leaves us with this final, massive question to think about. If engineers could figure out how to perfect room temperature superconductors, literally eliminating resistance entirely from our daily lives, how would that revolutionize the electronics of our future? I mean, with infinite, perfect electrical flow and absolute zero heat loss, what kind of incredible futuristic world could we build tomorrow based on these fundamental laws we explored today? It's an absolutely electrifying thought. Thanks for diving into this explainer with me.